Okay, so we finished homework 5 material actually at the end of last lecture, so today we're moving forward already with homework 6. And I think what we need to do is fairly obvious from here. We need to discuss where magnetic fields come from. So we've obviously talked about the magnetic field effects quite a bit at this point. That's kind of what homework 5 is all about. So magnetic fields, they can affect the trajectory of a charged particle. They can make that charged particle bend into a helix or a circle. Then we took a bunch of charged particles, put them in a wire. You can find the force on a segment of wire. And then we took that wire and we bent it into a loop. And we found there's some interesting things that happen with a current loop, right? We experience this torque to align in a particular way in a magnetic field, and we found all sorts of applications for that last lecture. So now we know all about magnetic field effects. Let's talk about magnetic field causes. So here's where I'm going to motivate it. So cause, effect, and let's talk about, again, comparing electricity and magnetism. So first of all, what was the cause of an electric field?
A charged particle.
A charged particle. We usually labeled it capital Q, right? And what felt the effects of an electric field? Another charge, which we usually labeled lowercase q. That's other charges, right? In fact, the electric field was just the middleman for charged particles interacting. So instead of letting them talk directly, which was Coulomb's law, instead what we had was one makes E, other one feels E, right? All right, so we know all about the effect side. So what do we find, what felt an effect from a magnetic field? Charge, but it was not just charge, it has to be moving, right? So a magnetic field can only deflect pre-existing motion. It can't pick up a charge from rest, right? Now we also found, of course, that it not only has to be moving, but it has to be moving either in whole or in part perpendicularly to the field, right? It has to cut across the field lines. But let me just say here, just to make the analogy as good as possible, let me just put here that the charge has to at least be moving. Yes, it has to be moving in a specific way, but it has to be moving, right? This whole idea is that the magnetic force is deflective only. It can deflect motion if it exists, but it can't pick up a charge from rest. It can deflect it into a circle or a helix, but it can't do anything with a charged particle that's sitting at rest. So, if we were to follow this kind of pattern here and try to fill in the missing blank, what do you suppose causes a magnetic field? Any ideas? That's one example. So if this is charge, this is another charge. What? Moving charge. So moving charge, that's right. So moving charge creates a magnetic field, and other moving charge feels an effect. Okay. Now that's, of course, not a particularly scientific way of doing this, but it does fit the sort of pattern, and I wanted to show you that pattern. So whenever a charge is moving, you see that it makes a magnetic field. So this brings up a kind of a conundrum. If we have, say, a charged particle, we have somebody holding it in their hand, that person would say that that charged particle makes an electric field. they're just holding it in their hand. That's the charge, so it makes an electric field. But, of course, motion is in the eye of the beholder. So if this person was also moving, and another person looked at that, they would say, and it makes a magnetic field too. Because to that person, that charge is moving. So who's right? Does it make just an electric field, or does it make an electric field and a magnetic field? They're both right. So what kind of field something makes is a relative opinion based on if that charge is moving with respect to you or not. Okay? So this gives us obviously a hint at the fact that there's a deep connection between electricity and magnetism. And in fact, we're going to, in a week or two, unite them into a common thing called electromagnetism. It turns out that that's one phenomenon. It's like, and electricity and magnetism are like two sides of the same coin. Okay? So it suggests a deep connection between them, which we will delve into later. Because motion is in the eye of the beholder, so is what type of field something makes. Okay? So that's getting a little ahead of ourselves. We don't want to unite electricity and magnetism quite yet. And in fact, we want to be able to look at magnetic field alone without having to worry about the electric field. Because then that's two things to worry about. So what I'm going to show you is a way where you can have a situation where something, the charge is moving, so it makes a magnetic field, but there's no net charge, so it doesn't make an electric field. Which, it sounds like, how could you do that? How can there be moving charge if there's no charge? Well, you can do that. Here's how. I'm going to have a wire which is carrying current. So current carrying wire. A current carrying wire is generally has no net charge. And the reason why is because it has, of course, a bunch of electrons that are flowing. But it basically has an equal number of positively charged nuclei that they're flowing past. So there's positively charged nuclei that these are flowing past. In this case, of course, strong the real motion of electrons. So we have this weird thing where, of course, the electrical current is defined as going the other way. Remember that it's really electrons flowing to higher voltage, but we take it electrical current as these hypothetical positive charges flowing to lower voltage. So we have that this wire overall has no net charge. It's a bunch of minuses flowing past a bunch of positives, and so there we can ignore the electric field. So a wire doesn't really make an electric field, a current carrying wire. But here's where we have our cake and eat it too, because if we're talking about moving charge, well, the positives aren't moving. So to us, they don't make a magnetic field, but the negatives are, and so we're going to see a magnetic field because of the fact that half the charge is moving and half the charge is not. Okay? So here, because the current overall is not zero, there's a movement of charge, we are going to see a magnetic field. So that's how we kind of have it both ways. We can examine only magnetic fields without having to worry about electric fields too, by focusing our attention on current carrying wires. So for us, there is going to be an intimate connection between current and magnetic field. Current is the type of moving charge that we look at, and it's going to create a magnetic field. Okay? And what we're going to spend the rest of today doing is looking at current in various configurations. We can shape wires in various ways, send current through it, And those various current configurations will cause certain magnetic fields, and we'll just take a look at that and see what the specifics are. Okay. Are there any questions on this before I get to it? Okay. So let's start with looking at our first current configuration. This is going to be the magnetic field of a infinitely long straight wire with a current I. Now, what does this mean? This means a wire that's straight like this, and it goes on and on and on forever in both directions. Now, you might question, why would we do that? There's no such thing as an infinitely long wire. Well, there are very long ones, to which this formula that I will give you is a highly accurate approximation. And you might ask, well, why do I start with this? Well, it isn't the first time we've had some weird configuration that's necessary to produce a field that's very simple. The first one was the infinite parallel plate capacitor. Remember that? We had to take two plates and make them infinitely long before we got a simple field. In fact, of course, it makes the simplest field possible, right? It's a uniform field. So this is kind of in that same spirit. We're taking something that has some kind of infinite dimension because it makes the field very simple. So think about it like this. If this is very, very long, we can never really run off the end of it, which means that there's no difference no matter where we are along it. It's not like we can get closer to the edge or further from the edge, so there'll be no change whatsoever to the magnetic field going along it because we can never run off the end of it and start to see a different field when we start to get closer to the end. So that's why we start with this one, because it's very straightforward. All right, so let's do it. So first things first, we need to address the size of it. And the size of the magnetic field will be given by this equation. I'll go through it and explain all the variables that are in it, but I'm not going to explain where this equation itself came from. Perhaps if you're in the supplement, in fact I'm sure of it, if you're in the supplement, you'll be going to some more fundamental laws where you can get all these things. But here, in the main lecture, I'm just going to give you a bunch of formulas. You're going to have to trust me that they give the magnetic fields, and you certainly don't have to memorize them. These are on the equation sheet for the exam, and in a little bit more detail, they're also on the magnetism summary sheet, so you can refer to that as well. Okay, so what are the variables? Well, current. That's obvious. You need current to run through that wire because that's what creates the magnetic field, those moving charges. And the more current you have, the stronger the magnetic field will be, all else being equal. So more current causes more magnetic field, and of course, vice versa, less current or even zero current will cause little or no field. Okay? The other factor, R, that's just proximity. How far are you away from the wire? So that measures at any point in space where you're interested in finding the field, how far are you from the wire? And hopefully it doesn't surprise you that as the distance increases, the magnetic field decreases. So as you get further away from the wire, the magnetic field is weaker. When you get closer to it, it's stronger. It's not a R squared, it's just R. B is proportional to 1 over r, which means, of course, that if you double the distance, you'll have the field. It doesn't quite fall off as fast as a point charge, right, 1 over r squared. And the reason for that, if you are interested in knowing, is because this isn't just a point, right, it's a whole line. And so it's got one infinite dimension, so the magnetic field is not going to fall off quite as fast. In fact, when we did the electric field stuff, we learned that if you extend it out to infinity, not just in one direction, a line, but 2 dimensions, a plane, we could get that the electric field doesn't drop off at all. It becomes uniform. So this is kind of like the intermediary point between a point charge, which is 1 over r squared, and a plane, which is constant. This is for electric field stuff, of course. But it's kind of the similar idea, right? It's kind of not all the current is condensed down to a point. It's extended infinitely in one dimension, so that makes the field fall off slower, but it's not extended out infinitely in 2 dimensions where it would be constant. So again, if that doesn't ring any bells or isn't helpful in any way, then can you just ignore that and just see this relationship in the equation. The final variable is mu naught. That's just a constant. It's called the permeability of free space. Now that sounds very similar to the epsilon naught, okay, which is called the permittivity of free space, or permissivity. This is permittivity or permissivity. Now again, I pointed out at the time that when I was introducing this constant that it's a very tantalizing name, and this apparently does as well. Why are they called that? We'll get to that later. But for right now, you should understand that this, in one form or another, is like our electric constant. So that appears in every single one of our electric field formulas in some way. It either appears as epsilon naught, for example, epsilon naught A over D is the capacitance of a capacitor, without a dielectric, of course. And it also appears in other forms in every electric phenomenon, because remember, K is just a repackaging of it, right? K is just 1 over 4 pi epsilon naught, okay? So epsilon naught appears in all of our electric phenomenon equations in some way. Well, mu naught, the permeability of free space, is going to be like our magnetic constant. It is going to appear in some way in all of our magnetic field formulas. It plays the same role for magnetism as epsilon naught, or its reframing K, does in the electric side. And so let me just tell you what its value is. And then later on, we'll figure out why they have these crazy names. The value is 4 pi times 10 to the minus 7th. And that is interesting in and of itself. This fundamental constant has pi in it. Seems strange. And then the units that have to make this equation work out are Tesla meters per amp. So hopefully not surprising, because Tesla's is magnetic field, that's in there, meters, that's in there, that's R, and amps is of course current. So if you want to all play nice, that's what the units of this constant has to be. Question?
So just to make sure I understand how to punch that into a calculator, it's 4 times pi times 10 to the negative 7?
Yes.
Okay,
cool. Okay, so that's the size, and then we of course have to address the direction. So I should have, well, I guess I'll go over here. let me just recopy my constant over here. 4 pi times 10 to the minus 7 Tesla meters per amp. So the direction. It's another right-hand rule. Okay? Well, I shouldn't say it's another right-hand rule, it's another use of right-hand rule number 2. There are only 2 right-hand rules, so you just need to know how to apply them. There's right-hand rule number 1, which again, just to remind you, is the slap rule, right? Slap one thing into a second thing, thumb gives a third thing, which is perpendicular to the first 2. Okay? We have 2 uses of that. Well, it's really, depending on how you count it, it's 1. But we're talking about the force on a charged particle, you slap V into B, thumb gives F, right? And then the other usage of it, where it's not just one charged particle, but it's a whole current, you slap the current into B, thumb gives F. So I kind of think it's the same thing, but if you want, you can count it as 2 different uses of slap rule. The second rule gets used quite a bit. It's the curly straighty one, okay? So this is it right here. It's easier to use because it's just a curly thing and a straight thing. So you curl your fingers around something and your thumb gives the other thing. Okay? Now, we've used that before. Of course, our first usage of it was the normal vector, right? So we have that the current went around the loop like that. We wrapped our fingers around the current, and the thumb gave something called the normal vector, which is nothing physical. It's not like there's anything really sticking out. It's just a convenient shorthand for how to describe the orientation of that current loop in 3D space. Okay? So here, the current was curly, and the normal vector was straight. And that's why they got assigned the way they did. Your fingers go around whichever is doing the curling thingy, and your thumb gives whatever points straight. The reason why I'm pointing that out here is because here, it's the current that's running straight, and it's the magnetic field that's going to wrap around it. So notice that the current just switched which one it got. Okay? So the current used to be your fingers, now your current is the thumb. That's why I call it curly straighty, because it's whatever's curling gets your fingers. So if the current's curling, put it on your fingers. If the current's straight, put it on your thumb. So in this case, it's the magnetic field that curls around it, and it's the current that actually runs in a straight line. So that's how you do it. You point your thumb along the current, and then your fingers will give the direction of the magnetic field that wraps around it. Okay? Does that make sense? So we can certainly, I guess I should probably draw you an expanded view of that. So here's the current. This is the current coming right at you. So not the perspective I drew at first, but the current is running right at you. It's going to run right through your eye. And the magnetic field is going to look like this. Let me try to draw it decently. I'm going to try to show that the field lines are getting further apart. I should probably have some color coding here, so let me, I guess, make the current be a different color. I'm trying to show the magnetic field lines wrapping around according to the right-hand rule number 2, and I'm also trying to draw the field lines further apart as I go further away from the wire. Why am I trying to do that?
It gets weaker.
It gets weaker, that's right. We found that it falls off with distance, right? So we should find that the magnetic field is weaker out here, so the line spacing is larger, and then here, let me try to draw them even more closer back here. Here, the magnetic field is stronger closer by. I'm trying to draw concentric circles, and they look kind of warped, but that's just because I can't draw very well. Okay. that's what it looks like from a head-on view. I think that's the easiest to see the right-hand rule, number 2. And then I should probably also draw it over here, where we get used to seeing it in the side view. So let me again color code the current so I can then do the magnetic field in black. So I can have the same colors coding here. So let's try it now. I point my thumb along the current, and if I point my thumb along the current, everywhere up here the magnetic field is going to come out of the page, and then it's going to go into the page below, right? See that? So if the current goes like this, the magnetic field wraps around it, so it comes out here and in here. It's basically a side view of this, right? So if I'm looking at the current coming by like that, right, going like this, I'd see this coming toward me, and I'd see this going away from me, okay? So let's try to draw that. And I'll do more. It'll kind of look like that. Don't have room for much more. I do want to point out in this picture, I'm trying to have the field lines get further apart going this way because, of course, the magnetic field is decreasing. The magnetic field decreases as you get further and further away. So you should try to have those magnetic field markers get further and further apart. But it should not change spacing going this way. Because if you're going along the wire, you're not changing your distance from it, right? You're still at the same R value. You're still equally far away over here as you are when you move over here. So here, the spacing should be consistent, right? So the magnetic field has a constant size if you just go parallel to it. Does that make sense? Because again, you're just exactly the same distance away from the same current, and you shouldn't expect any changes along a current that never ends, right? You're not getting it closer to the end. There is no end, right? Okay, so that's our first magnetic field, and it's definitely also our workhorse one because it's one of the easiest things to find anywhere you want. And so what I'm going to do next is I'm going to simply do an example problem. This is the classic example problem for this. And this system is a source of an immense number of problems that I either give you or could give you. So I'll try to talk through all the possibilities. I'll basically tell you all the different things that I can put on the exam pretty much. Okay? So let's do an example with this one. Then I'll go on to other currents, and of course, what other current configurations, how would that magnetic field change? If you have some kind of ability to draw in different colors, it's going to be really useful here. So if you have different colored pens, that'd be great. If you just have a pen and a pencil, maybe that will do. So let me go ahead and draw my system. Try to get a nice dark color, like dark red. So pick one color for the first wire. I'll call that I1. And then pick another color for a second wire. I'll call that I2. So what I have is not one, but two parallel wires. And here are the givens in my example. My givens are I1 and I2. So consider those just like numbers that haven't arrived yet. These are things that are allowed in the answer. And then I'm also going to give you D, which is their separation. So if they run parallel to each other, how far apart is that? That's the distance D. So with those givens, here's my questions. So I'm going to ask, what is the force on wire 2? And it turns out that as far as measuring the force, we're not going to quite measure the force. We're going to measure a related quantity, but I'm not going to tell you that yet. I want to bring it up when it becomes obvious. What's the force on wire 1? And once I've done that, talk generally speaking about B net in the region. Okay? So that one won't be quite as much as like an example problem. It's just kind of generally pontificating about the system. Okay, so let's go ahead and get started. Let me go ahead and sketch the magnetic field. Let me start with the magnetic field of wire 1. So basically have it over here. So I point my thumb along the current, my right thumb. So the magnetic field everywhere above is going to come out of the page, and everywhere below it's going to go in. So I go ahead and I sketch that. I'm going to do it in the same color as the wire that made it, so that I can kind of keep straight what's going on. If you don't have the colors, you're going to have to label that B1 somehow, and you're going to have to kind of sort it out later, because there's going to be a lot going on here. Everywhere below, we said it goes into the page. And I'm purposely drawing it on top of wire 2, because of course, that's what wire 2 is going to feel. It's going to experience the local field where it's sitting, and that is made by wire 1. So let's start there. If I want to know the force on wire 2, where does that force come from? It comes from wire 1, right? Magnetic field, in general, is just the way it is a middleman for interaction, right? Now, why don't I need to draw the magnetic field that wire 2 makes for this?
That's not what you're asked for.
That's right. And specifically, if I'm asked for the force onto, do I need the field that it makes? No, you can't pick yourself up anyway. Your own field is for interacting with other things. You can't be your own force, right? You can't make a field and then feel a force back from your own field. That doesn't make any sense. It's like picking yourself up and carrying yourself out of the room. That's generally the idea with fields, right? The idea with fields is that you make fields for others to feel, not for yourself to feel. So in this case, the force that wire 2 feels is from wire 1, and the way that we take care of that is by identifying the field that's made by wire 1 and then seeing what wire 2 thinks about sitting in that field. So let's go ahead and figure that out. The force on wire 2. So, this is something that is on your current homework, right? We know we're good on the effects side, right? We know that how much force does a piece of wire feel? Well, the formula is ILB sine theta. Now here we have to be really careful about what I, what L, what B, all that stuff. So the force that a given wire feels is due to the current that's in it, its length, and which field? 1, right? It can't be your own force for your own field, okay? So the amount of force that wire 2 will feel has to do with how much current's in it, how long is it, and what field is it sitting in, and we know that field is from the other wire. And this will be the angle between I2 and B1. So I guess let's get the angle out of the way. What's the angle between I2, so that's the green, and B1, which is like that? 90. Sine of 90 is 1, so we get the maximum amount of force, right? It's because this current is cutting perpendicularly across the field lines of the other. Now, here's one issue that I'm going to have right away. We said that this wire was very, very long, right? So if it is infinitely long, we'll get an infinite amount of force. That's kind of a little bit of an issue, right? Now, does this have to be infinitely long to do the problem, or the current problem that we have, the current calculation? No. I mean, if we had this had a finite length L, we just put it in. This doesn't really have to be infinitely long for the purposes of feeling a field. But it does have to be infinitely long for the next part, because of course we can't calculate the field that it makes without having it be infinitely long, right? So for feeling a field, so feeling an effect, L does not have to be infinite. Or I should say, that says, it should say does not have to be infinite. But for causing a field, it does. Because we only have the formula for an infinitely long current in terms of making a field. So we run into kind of a unique problem in this, or a unique issue in this particular problem, because we're asked about both ways. And so we kind of have to have our cake and eat it too, because we need them to be infinitely long to know the field that they make, but we need them to not be infinitely long for the force they feel. How do we get around that? Well, we'll solve for the force per length. Okay? So this is the force felt per unit length. So how many newtons of force does it feel per meter of its length? That will be a finite number, and if we find that it's 10 newtons per meter or whatever, that means it feels 10 newtons of force for every meter of length. And if it happens to then be infinitely length, then yes, it'll feel an infinite amount of force, but it still makes sense to talk about how much force is felt per unit length. So what we're really going to ask for here, just to make this sensical, is force per length. Okay? So let's go ahead and find what we get here. This is I2 times B1. That's going to be a perfectly fine number. It's not going to blow up and be infinite or anything. There's a finite amount of current in wire 2, and there will be a certain amount of magnetic field that's made by wire 1 at wire 2's location. And this is where we deviate from your homework 5, where in homework 5 I would have just had to hand you the magnetic field and just say it's whatever, 5 Teslas or whatever it happens to be. Now we are capable of figuring it out ourselves. So we go ahead and we say the magnetic field made by wire 1 depends on mu naught, the current in that wire, and how far are we away from it. So how far are we away from wire 1 when we're at wire 2? 2D. So we go ahead and just put that in here. And we get F2 over L2. Let's consolidate. Mu naught I2 I1 over 2 pi d. Now, that may not look like an answer per se, but let me remind you that that is an expression involving only givens, the two currents and d. And then, of course, mu naught and pi, those are constants, so those are always allowed. So that's the force per unit length that wire 2 experiences from wire 1. Now, that's just the amount. We should also probably find the force direction, so let's use our good old slap rule. So take out a right hand. We point our fingers along I, we figured out how to orient this so that we can slap I2 into B1, right? So I2 slapped into B1, force is going to be like that. So this will be the force direction. What we find is that wire 2 will be attracted to wire 1. It gets pulled towards it. All right. So that's the first part. Are there any questions before I do the same thing but in reverse? All right, so let's do that. So whatever color you put wire 2 with, now we're going to use that same color to do the magnetic field that it makes. So we're going to now do the magnetic field of wire 2 because wire 1 is sitting in it, and that's how it's going to affect wire 1. So we point our thumb along the current, and the magnetic field curls around it. So everywhere above this wire, it'll come out of the page, and everywhere below, it'll go in. Let's sketch that. Etc. Good enough. Let's really see why we want colored markers at this point, because otherwise you're going to get totally lost as to which of these goes with which wire. So I drew it everywhere, although I didn't really have to. I really kind of drew it everywhere for a later discussion. But the only place I really needed to draw it was on top of wire 1, because of course wire 1 feels the effect from that local field. Just where it's sitting, it experiences some field. So let's do it. This will proceed very similarly to what I did before, so let's just see how it goes. We want to now define the force on wire 1. So we use good old ILB sine theta. And try to do this without peeking at the other side. Which current should this be? Should this be current 1 or 2? 1. This should be length 1 or 2? 1, right? Magnetic field 1 or 2? 2. So the amount of force that wire 1 feels has to do with the amount of current in it, its length, and the magnetic field that it feels, which is not from itself, but from something else. Okay? And this is the angle between I1 and B2. All right, let's get that angle. Let's start there. I1 points this way. B2 points this way, right? So what's the angle between I1 and B2? 90. That's the angle between the current and the magnetic field that will be pulling on it. So sine of 90 is 1. So run into the same problem, right? That the amount of force will be infinite simply because the length is infinite. So we'll solve for something more manageable, find the force per unit length. So what was a plus in terms of finding the field made by wire 1 for the last part, the fact that it was infinitely long made it easy to find the field. But now it's, of course, a little bit of an issue with getting the effect. So we instead solve for the force per length. So that'll be I1 times B2. And again, we don't have to speculate. We don't have to get handed on a silver platter what is B2. Okay? We now know how to solve it. It'll be the amount of current in that second wire and how far do we happen to be from that second wire. So how far are we away from wire 2 when we're at wire 1? D again. So what do we find? get this. What do you notice about that compared to this? It's the same expression, right? It doesn't matter what order the currents are multiplied in. Okay? Let's find the force while we're at it. Let's do the slap rule. We have to slap I1, which is this way, into B2, which is this way. So which way is that force? It's down, that's right. So I1 slapped into B2, force is down. So we found that wire 2 attracts wire 1, while wire 1 attracts wire 2. They're mutually attractive. And we found not only are the forces attractive, but they're exactly equal in size. This seems like a prime example of what? Anyone remember from physics 1, when two forces are equal and opposite? Anyone remember that law? The third law, Newton's third law, that's right. Newton's third law. For every action there is an equal and opposite reaction. It still applies here. Okay? So if one object exerts a force on the other will feel an equal and opposite force back on it. Okay? That's what we're seeing. We're seeing mutual attraction. When two wires run parallel to each other in the same direction, they will attract each other. And once you found the force on one, the other one will feel an equal and opposite force. It was nice to see it come out of the calculation. It was good practice, but we could have just written it down. Okay. Are there any questions on that? So, in this case, because the currents are running the same way, they're attractive. Try it at home. Try having the currents go not in the same direction, but have them go parallel, but or anti-parallel as we call it, right? Parallel to each other, but in opposite directions. You'll find they repel. Work through that, right? So, two currents that go in the same direction will attract. Two currents that go in opposite directions will repel. Right? Okay, so we've knocked off these two. Let's talk about B net in these regions. Now, of course, you would have no use for B net, which is the sum of these two, unless you were talking about putting a third thing in here, right? Because you would never sum up these two fields and then apply it to one of these, because then that would involve double counting something. It would involve taking a field that something makes and putting it back on it, right? But it might be useful to discuss B net. Let's say if we threw a charged particle into this region, right? Say a third object. Well, this third object would be affected by the other two, the two things that are already here, the two wires. So we could look here at B net. There it's pretty obvious. What's the direction of B net there? They're both out of the page, so B net's out of the page. They reinforce each other out there. Over here, what's the direction of B net? Into the page, they're both into the page. So things get more interesting when we're between the wires, right? So there, it of course depends on which one's bigger, right? If the one that's out of the page is bigger, then net will be out of the page. If the one that's into the page is bigger, then it'll be net into the page. It could even also be 0, right? If they cancel, exactly. So we can go back to some of our intuition about fields that we did on homework number 1. So if you remember homework number 1, right, we had these two charges on opposite sides, and we were asked, where's the net field 0? Or I think I might have asked, what's the force is 0, right? Same thing, right? If the field is 0, the force is 0. If these two currents are equal, where do you suppose the net field will be 0?
Right in the middle.
Halfway. What if one of the currents was much bigger? Where would the 0 point be? Closer to the smaller one. You've got to give the smaller one something to go for it, right? So you got to be further from the big current and closer to the small current, right, if you want them to cancel. So there will always be, somewhere in here, a point where B net is 0. So B net is possible, but it's going to be halfway in between only if the currents are equal. Otherwise, it's going to be closer to the smaller current, right, whichever way that is. Is this kind of ringing a bell in terms of thinking about fields? So I'm just kind of giving you really quickly a bunch of different problems that I could ask you, right? Could the net field be, the net field could never be 0 on the outsides, right? Because the fields are reinforcing. It can only be 0 somewhere between them, right? In this particular current configuration. Now, one of the things I could do, again, I could go back to that system where the two are running anti-parallel, right? Not the same way, but parallel in opposite ways. Well, what would happen then is that the magnetic field would reinforce in the middle and point opposite on the outsides, right? So I guess I can quickly sketch that out. If you had the two currents that were running like this, whoops, that's the same thing. What you would find is that both the magnetic fields would reinforce here, and they would oppose out here. Let me ask you this. If the currents were equal, could the magnetic field cancel here? How? How could they be equal in strength? The currents are the same, but what's the problem? You're going to be closer to one than the other always. It's possible on one side for them to cancel if the currents are unequal. Which one has to be the smaller current, the top one or the bottom one?
The top one.
Top one, right? Because you have to have it having, you have to have that you're closer to the smaller one and further from the big one. It can never cancel over here, right? Because you're going to be closer to the bigger current. Okay, so those are just a bunch of different things. The system has many possibilities. You'll see some of them on your homework, and you'll see some of them on the exam for sure. So I know I went through a lot of those permutations fairly quickly, so just go through them at home and convince yourself of them. And kind of work, once you've worked through all the permutations of the system, there's not a whole lot left. So work through the currents being the same way, work through the currents being opposite, work through them being equal currents, work through them being unequal currents, and then ask yourself, where is the net field? Never 0, could be 0, always 0, all that stuff. Okay, are there any questions on that before I move on to the next current configuration? All right. So my next current configuration is going to be the magnetic field of a wire loop. It's going to be circular with radius r. It's going to have a current I, and this is going to be a complicated enough field that I'm going to ask only in the center for you to find the magnetic field. Okay, so only at the very center of the loop, not just any old point. So I mentioned before that the last one we just finished, the straight wire, is nice because I can ask you the magnetic field anywhere. It's easy enough to do that. This is not, so I'm going to have to restrict my interest to a single point. So that's what I'm going to find. I want to know what's the size of that magnetic field at the center of the loop. And I want to talk about the direction as well, of course. All right. So let's kind of imagine forming this out of a segment of straight wire. So we just finished that. So we have a current went on like this. Magnetic field is out of the page over here, and it's into the page below it. So we're just going to imagine coming up to this with a pair of scissors, right, and just snip, snip, and then bend the wire. Okay. So I'm just going to go like that. So we grab a segment of it and do that. So we can still use the right-hand rule on this. If you, of course, this top segment looks just like this. I should probably switch to a different color. So that looks just like this. And then just kind of follow that along, etc. Basically what we've done is we have trapped the magnetic field lines that are going into the page in the interior of the loop, and the magnetic field lines that go out of the page are on the outside. All right? And so what I'm going to ask is, what is the magnetic field right here at the very center? Right? Oops. I'm going to put a dot there because it's going to make it look like it's out of the page. Let me just circle it like this. This is the point where I want to find the magnetic field, right at the center. I said I would do this in a circle, so the radius of my circle is going to be capital R. Here's my formula, and again, you'll just have to take my word for it. Mu naught I over 2R. That is how you find the magnetic field in the center. You have to ask what's the amount of current. So obviously more current means more field. And then R, make sure it's capital R, because capital R is the fixed radius of your loop, of your circle. Okay? So when you're increasing R, what you're doing is you're actually making your loop larger. So if you make your loop larger, it shouldn't be any surprise that the magnetic field in the middle is smaller. Because of course if your loop is very large, then being in the center means being pretty far away from the wire itself, right? Whereas if it's a very small loop, you're quite close to the current when you're in the middle. Okay? So that's it. That's your formula. And one modification that I'll make to it is that sometimes you don't want just one loop. We saw that there's some use to having a bunch of loops. So very often you might want to be open to the idea that you have a couple loops. So this is N is the number of loops. This assumes that you have few enough loops that they are basically, you're able to get them all kind of in exactly the same place, right? So this is not too many. Just because in practice, if you have 1,000 loops or whatever, you can't fit 1,000 terms of wire into exactly the same place. It starts to make a coil, okay? So this might be good for 2 or 3 or 10 or whatever, but it's not good for lots and lots and lots just because it starts to form a tube, okay? You can't get that many turns into the same physical space. Question?
Would we ever need to know multiple loops with different radius?
I guess if you, as long as they share the common center, then you would just add the equations, right? So if you had like one loop like this with some current, and then you had another one like this, then you would either add the fields in the middle if they were reinforcing, or you would subtract them if they were opposite, right? They could have different currents and different radii, but they would have to share a common center because we can only find the magnetic field in the center of a loop. We can't find it in other places. So the principle of superposition that we use for electric fields, we can use it here too. Okay. So direction. Let's talk about that. Well, you can use that right-hand rule. Obviously, you can point your thumb along any segment of the current. Just pick your favorite one, and you'll get an answer. The magnetic field will go into the page here, or it'll come out of the page on the outside. Just apply that. Or here's another way to do it, a shorthand. You know how to find the normal vector, right? You wrap your fingers around the current. This is a current loop now, so you wrap your fingers around that. The normal vector would point this way, and hey, that's the same direction as the field. So that's convenient. So the direction of that is the same as the normal vector of the loop. In fact, what I'm going to attempt now, and I do emphasize attempt, I'm going to try to draw a 3D view of this. Sometimes this goes better than other times. So this is like kind of a flat plane view, like just looking dead on at the loop. I'm going to try to draw a 3D view. 3D view. Here I go. So here's the loop. And that's my attempt to make it clear which side is more toward you and which one's not. You see what I'm trying to do there? A little bit of 3D perspective. That's better. Okay. So the current's going to go down like this, and it's going to flow up this side. So it flows around like that. So here's my attempt to draw the magnetic field. Do a better job than me. It's not the worst thing I've ever drawn. Let me try to not mess it up anymore. That's the magnetic field overall. So you can see they form these kind of closed loops. It kind of is like a donut almost, right? So magnetic field lines go through one way, through the interior, and then come out the other way. Okay? So you can see that here. If I were looking at this at a flat view, right, I'd see the magnetic field lines go through in one direction and then come back at me on the outside in the other direction. So they're forming closed loops. And by the way, we'll find, we won't have time for this today, but we'll find the magnetic field lines always form closed loops. Okay? So this is just really a crosscut, but magnetic field lines always connect. So they were already looping around a piece of straight wire. But now that we've taken that piece of straight wire itself and made it wrap around, we have that the magnetic field lines form closed loops and kind of donut around it. I guess what I should probably do is wrap my fingers around the current. The normal vector points like that. And as advertised, the magnetic field through the center of the loop is pointing that same way. So you can see that all of these come out, going to the right. That's the magnetic field at the center. Now here's a quick question for you. It seems like we have a bit of a paradox here. We made a big fuss about the normal vector as a means to talk about how a current loop likes to orient in a field, right? We learned that the normal vector likes to align with the field, and if it isn't aligned that way, then it'll torque until it does, right? That's a big part of homework number 5, right? This idea that a current loop will experience a torque until its normal aligns with the field. And yet here I'm saying that the normal vector and B are in the same direction always. So why is that not a complete contradiction? What's going on there? Does anyone know? So again, we talked about the normal vector wants to torque to align with the field, and here I'm saying the normal vector is always aligned with the field. What's going on? What's that? It can't, if the current flows around this way, the normal vector has to be like that. And if the current was flowing the other direction, well, the normal vector would point that way, but so would the magnetic field.
It can't move itself.
It can't rotate itself anyway, that's right. So this is a handy mnemonic, but this magnetic field is not eligible to act back on the thing that made it anyway, okay? The normal vector is useful when talking about how a current loop reacts to somebody else, not itself. So if we applied a magnetic field from some other source, this normal would for sure want to align with it. If we applied a V external in this direction from somebody else, you better believe that this loop is going to torque so that the normal wants to align with it, and it'll take the whole magnetic field that it itself makes with it, okay? So this is just handy as a way to remember the way that the magnetic field points toward the through the center, but the normal is, of course, used for interaction with other things, right? I'll just put others. It's not eligible to, so your own normal and your own magnetic field are like not things that are ever going to have a chance to directly communicate, right? Your own normal is for how you react to other things, and your magnetic field is how other things react to you, right? Okay. That is the second magnetic field that I will talk about. You can see it's quite complicated. You can generally see it gets weaker as you get away from the thing, but that's kind of just conceptual. It'll be quite strong in the middle because you're, of course, fairly proximate to a lot of current. But the only place where I can actually ask you, hey, how many Teslas is it, is in the center, okay? Other places, I can't ask you what the number is. So the final orientation that we need to look at of current is what happens if we start to have so many turns that we can't possibly conceive that they can all be put in the same space. We have so many turns that it starts to form a tube. So we have this very long tube of current loops. That's called a solenoid. So let's talk about that. So what is the magnetic field of a solenoid? That is a very long tube formed by current loops. So it might look like this. Let's try to see if I can draw that. your currents. And the tube goes on and on and on. Now, you don't really have to do this by stacking a bunch of independent currents. One of the easiest way to do this is just by winding one wire around and around and around and around. They don't have to be independent. So they could be independent, but we could just take one wire and just wind it around and around and around again. So the question is, what is the magnetic field of this thing? Looks like I'm not going to get to that today, so let's pick up there next time.